Hello everyone. So today we are going to start off with a new topic called matrix, which is a part of mathematical physics. So in mathematical physics, matrix is basically a rectangular or a square array of numbers or symbols arranged in the form of rows and columns. Matrices are usually widely used to represent and solve systems of linear equations which frequently arise in physics problems. So they provide a compact and systematic way to handle multiple variables, equations, and many more functions. So matrix is basically essential mathematical tool which helps physicists to solve and model various physical systems in a clear and organized way. Matrix also plays an important role in many areas of physics, such as quantum mechanics, electrodynamics, classical mechanics. For example, we need matrix in transformations, rotations, and operators can also be represented using matrix. So, by applying multiple matrix orientations such as addition, multiplication, and finding determinants, complex physical problems can be simplified and solved efficiently. So, we'll do matrix today. So, as I have already said, that matrix can be of anything, like it is a rectangular or a square arrangement of anything. So, it can be alphabets, numerical figures, symbols. For example, this can be a matrix x, y prime, d. This can also be a matrix at the rate, hash. Similarly, this can also be a matrix. It can consist of numbers 3, 4, 7, 10. So, a matrix can basically consist of anything. Now, there is a particular way to represent a matrix. We initially first write the number of rows and then put a cross and then write the number of columns. So, for example, if a matrix consists of m rows and n columns, we write it m cross n. So, number of rows cross number of columns, rows cross columns. Also, there's a particular way of representing the elements of a matrix. So, elements are usually represented as A is equals to Aij m cross n. Again, this m is nothing but number of rows, n is nothing but number of columns. Now, any two matrices can be added or subtracted if they have the same number of rows and columns. That is, for example, if A is equals to 1, 2, 3, 4 and B is equal to 7, 8, 9 and 10, only then can we add A and B because they have the same number of rows and columns, that is 2 rows 2 columns for both the cases. Again, they can also be multiplied only if the number of rows or number of columns of A is equal to number of rows of B. So if A has 2 rows and B has 2 columns, only then can we multiply A and B. Now, as matrix is an arrangement, we can't directly get its value. So comes determinant. What is determinant? Determinant will now see how to find determinant of a matrix. Now, in order to find determinant, we first need to find cofactors. So, what is a cofactor? In order to find a cofactor, what we need is cofactor is nothing but minus 1 to the power number of row plus number of column into minor. Alright. Now let us look into some of the properties of determinant. So property number 1 says that if all the elements of a row or column of a matrix are 0, then the determinant will also be 0. Property number 2 says that if any two row or column of a matrix are identical, like they have the same elements, then its determinant will also be 0. Property number 3, for example, suppose let us look into some examples for point number 2, property number 2. For example, if a matrix have A, B, C, D, E, F, G, H, I, and we write is equals to 2 into P, 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 Q, Q, P, R, R, 0. Alright. Then the determinant of A, suppose this is matrix A, whose determinant is this, whose matrix form is this, then the determinant of A would be 0. Now coming to the next property of determinant, we can say that determinant of A plus B is not equals to determinant of A plus determinant of B. Alright. But next property says that determinant of A, B is equal to determinant of A multiplied by determinant of B. Alright. Let us look into an example of this. For example, consider a matrix A is equals to 1, 1, 1, 3, and another matrix B which is 1, 1, 1, 5. Alright. So determinant of A would be, we know how to find the determinant. We cross multiply 1 into 3, which is 3, and subtract it with 1 into 1. So basically this into this minus this into this, right? So which is 2. Now determinant of B in a similar way would be 5 into 1 minus 1 into 1, which is 4. Alright. Now A plus B. So finding modulus of A plus B, that is determinant of A plus B, would be, let us first find the matrix for A plus B. So the matrix for A plus B would be 1 plus 1, 1 plus 1, 1 plus 1, and 3 plus 5, right? So this would give 2, 2, 2, and 8. Alright. Now modulus of A plus B would be, that is determinant of A plus B would be 8 to the 16 minus 2 to the 4. So which is 12. Alright. Now if we look into the determinant of determinant of A plus B is coming to be 12. Now what if we look into the determinant separately? Determinant of A separately is, where did I write A? Yeah. So determinant of A is nothing but 2, right? And determinant of B is nothing but 4. So determinant of A is 2. Sorry. And determinant of B is 4. So we can easily make out from this that determinant of A plus determinant of B is not being equal to determinant of A plus B, because 2 plus 4 can never be equal to 12, right? Now what if we multiply AB? So let us multiply AB. A is 1, 1, 1 and 3. B is 1, 1, 1 and 5, right? So multiplication would be this row and this column multiplied, again this row and this column multiplied, then again this row and this column multiplied, and this row and again this column multiplied. Alright, so let us multiply it. This gives 1 plus 1, 1 plus 5, 1 plus 3 and 1 plus 15. So 2, 6, 4 and 16. This is our AB. Now determinant of AB would be 16 2s are 32 minus 6 4s are 24, which is equal to 8, right? So now see, the determinant of A was 2, determinant of B was 4. So if we multiply determinant of A with that of B, it comes out to be 2 into 4 is equal to 8. And also determinant of AB being equal to 8. So we prove the fact that determinant of A into determinant of B is nothing but equal to determinant of AB. Alright. Now there are basically some more properties of determinant. For example, what does our next property say? It says that determinant of A inverse is nothing but determinant of A and inverse of that. Similarly, another property says that determinant of A transpose is nothing but determinant of A. Alright. Now, if a square matrix A is of order n multiplied by a scalar k, then we can write determinant of Ka, where k is the scalar, A is the matrix, alright, is nothing but equal to k to the power n multiplied by determinant of A. Now what is n? N is nothing but the order of the matrix. Alright. Now let us prove this property, last one, with the help of a matrix. So consider a matrix A is equals to 1, 1, 1 and 3. Alright. So determinant of A is what? nothing but 3 minus 1 is equals to 2. Now consider 2a. So what would be 2a? 2 multiplied by 1, 1, 1 and 3. Now multiplying it, we get 2a is equals to 2, 2, 2 and 6. Alright, now determinant of 2a is nothing but 6 2s are 12 minus 2 2s are 4. So this gives us 8. Alright, now determinant of 2a is nothing but 2 to the power 2 into determinant of a, because 2 to the power 2 is 4, determinant of a is 2, which is 8, which is again the determinant of 2a. So what is 2 to the power 2? 2 to the power 2 is nothing but 2 to the k to the power n. Alright, where k was the constant, we are multiplying with the matrix, and n was the order of the matrix. So here k being 2, n being 2. So this is not 2 to the power n, this is k to the power n. Alright. So we have come to the end of the determinant properties of matrix. On the next video, we will talk about the types of matrix. Alright.